Poincaré said this, and about just before the turn of the century, the previous century. And I'll explain a little bit about what his concern was. You should know, a lot of people should know this. Poincaré was one of those people with a kind of acid pen. He really liked being sarcastic when he said things like this. So this is not untypical of him. So, but when I ran across the quote, I just couldn't resist filing it away and saying, I need to use that at some point. So you're the victims. You get to hear this. So what I'm going to do is talk about this approach to topology. I'll try to explain why it's not the same as point set topology, which is what Poincaré was complaining about, why you would want to do it in the first place. And then we're going to develop the theory of locales in a way that will not be terribly familiar even to the frame theorists that are sitting in the back of the room. This locale theory is really pretty mature at this point. It's been around for a while, almost 100 years from Erisman. But I'm taking a little bit different take on justifying it and trying to figure out why it makes sense. Also, I kind of rewrote some of the talk today based on what I learned yesterday and what I learned last week in the seminar, namely the concern about what is the status of points? What are points in a topological space?
Sorry. Poincaré quotation is exactly this one, like point set topology?
Yeah.
I believe that it was a paraphrase. No, it's exactly.
No, he said, yeah, well, I mean, it's in English. He didn't say it in English.
Oh, of course.
But no, the subtitle is mine, but the main title is his.
Fantastic.
Yes.
Okay.
Yeah, absolutely. I wouldn't have the guts to title something that on my own. It had to be a quote from someone else. Yeah, so I rethought some of the talk based on the seminar when the question of what are points, what's going on at the apex of a light cone, that was the question that came up, and whether, as Marco pointed out, that had as much to do with approaching the point as it did to what is the status of the point itself. So I'm going to give you, after we develop this theory of locales, I'll give you 3 alternative notions of what a point might be. And I want to emphasize that these 3 notions they would conflate, they do conflate in point set topology. You can't really tell them apart. One of them you can, but the other 2 are really just the same if you're doing things in the classical point set topology that Poincaré was unhappy with. So that's a small philosophical motivation for thinking about locale theory, is it allows us to make this distinction between 2 different uses of the notion of point. And I'll explain that as we go along. So this is just not meant to be history. This is just breezy, set up the trail of thinking. Poincaré introduces this fundamental group of a space, of a topological space, and then recognizes pretty quickly that that is a thing that allows us to start classifying features of spaces. So using this fundamental group, you don't need to know what the details of that means, but it allows you to see that there is a difference between a torus and a sphere. We all know there is a difference between a torus and a sphere, but the fundamental group actually distinguishes the 2. So this is a pretty important, valuable thing to do. Or those 2 are also distinguishable from the punctured real line. So these are all 3 different spaces, and you can see that they are different spaces by virtue of their fundamental group. So this is something he did. And that really, his thinking on that really launched the 20th century fields of homology, cohomology, and what we now generally put under the umbrella of algebraic topology. So it's fair to say that Poincaré was the impetus for this really quite important, rich part of mathematics. And in it, he was thinking about the cube as being really, well, look, as a space, it's really no different than a sphere. If you're thinking about only continuous functions, if you're thinking about differentiation, it's a different story, right? Because then you have corners on a cube. But if you don't care about the discontinuity that is introduced in differentiation, you just care about continuity simpliciter, then these are the same. And a cube is the same thing as a sphere. That's the same thing as a tetrahedron. They're all the same, right? It turned out he studied cubes. He thought about cubes first. later on, it was pretty quickly realized that they were a little bit awkward. Behavior is not so great when you're putting cubes together, pasting them together to make bigger spaces. And triangulation is a better way to do it. So tetrahedra are better than cubes in a certain sense.
When you speak of cube space, you're speaking of three-dimensional space?
Yeah.
Or you are
yeah.
generalizing also?
No, he would certainly immediately you're generalizing to other things. So cube meaning a cube in Rn, okay, whichever n you're concerned.
The cube is simply n with equal, all the member equal.
Yeah, yeah. Okay. And in fact, it doesn't matter that they're equal, right? I could have a block, and for Poincare, that would be the same space. And that was an irritation because now you have two different spaces, but they're behaving precisely the same. And so part of what Poincare was interested in, what he was pointing out, is that distinction isn't very useful. That's been a thread throughout 20th century mathematics. And Jonathan knows a lot about that because that's what univalent axioms are trying to address as well, right? So this is in a long tradition. So for Poincare, the points themselves just weren't relevant to what he was interested in. And other people not doing topology per se, but pretty early, even Cantor, as Marco pointed out to me yesterday, saw that a theory of integration doesn't depend on the points, because I can pluck points out of a function and move them somewhere else, and the integral will still be the same. And I can do that with at least finitely many points. And then the question is, well, how many points can I disturb? And Lebesgue gives a really nice, firm answer that once you tell me what the measures of sets are, which sets are measurable, then integration is going to be invariant up to removing null sets, moving points around in null sets. But the point of that is that well, it means that the points of the space weren't relevant in the first place, if that's your concern. Behavior of functions doesn't actually reside on the points. It seems to reside on the structure of the space. That is part of Poincaré's complaint, is that we seem to have these points here, but we don't really want them and we don't need them. So along comes about, I don't have a date for this, I should, sorry about that. Erisman in the 30s, I don't know the exact date, said, well, look, this suggests that we really shouldn't be thinking of a space, that a profitable way to study a space is by studying the structure of its spots, of its open spots in particular. So this is the phrase that Alice Perlter likes to use for these things. Spots are things that are kind of macroscopic. It's not a point, it's a blob that I can see, at least at some resolution. It might be quite small, but it's still a thing I can see in a certain sense, right? And to describe a space is to describe the structure of those spots. And to study a space is to study those structures. Study spaces is to study those. So this was Erisman's idea. He wrote a few things about it. He called them local lattices. Nowadays, we call them either frames or locales. Same, those are synonyms for most purposes anyway. And he wrote a little bit about it, but it didn't get very far. And I'm going to skip past a whole bunch of other history. There's some important things that happened with a few people in the 1960s and 70s. John Isbell is really important. I think I mentioned him a little bit. Two other developments that happened almost concurrently with Erisman was that Stone was interested in a completely different problem. It looks like a completely unrelated problem, which is that if you have a set of sets that are closed under complement and union and intersection, actually just complement and union is enough, you have something that you could call that is a Boolean ring. It's a ring in which the multiplication is idempotent. That's what's meant by a Boolean ring. So in other words, you take any family of sets that has this nice structure and you automatically give yourself a Boolean ring. So his question was, well, do all Boolean rings arise that way? And the answer is yes. And the way he found the answer was by topologizing the problem in the first place, point set topology. So he was able to construct a Boolean ring from any topological space And then he was able to characterize those topological spaces that, as it were, characterize the Boolean rings. And they are these really weird, from the point of view of somebody who's thinking spatially, zero-dimensional compact Hausdorff spaces are very strange little gadgets. They're not the kind of things that an analyst would necessarily come up with on their own, because being zero-dimensional winds up meaning they're completely disconnected. So all the points are, so to speak, really far apart from one another. So it's quite strange little spaces that seem unnatural if you're thinking about algebraic topology, for sure. They just wouldn't arise for Poincare. Nevertheless, Stone saw the value in thinking about algebraic problems in topological terms. And this is a really important result that's really quite influential in the development of 20th century mathematics, and for a lot of people, I think that's fair to say. And it launched a lot of other things. A little bit after that, Wallman wrote a paper trying to study separation axioms in topological spaces. A separation axiom is something that says, how much information can I have about how one point is distinct from another point? And you can put different, you can have stronger and lesser separations, meaning there's more or less information about how far apart the points are. And he identified a separation axiom that's called subfitness nowadays. He called it the disjunctive property, which is a horrible name. And I would like to start calling it the Wallman separation. I think that's a good name. So Wallman spaces would be a good name for them. At any rate, he found them by studying, well, the dual of Aragon's lattices. The lattices of closed sets of a topological space. You won't see Wallman separation if you're staring too closely at the points. You will see it as a structure of the lattice. So that's another example where the points actually got in the way of understanding something that turns out to be really, really useful. So so these are all happening in the 20s and 30s. Stone's paper was 34 or earlier.
34, 36.
Somewhere in there. I wasn't alive yet. Doesn't matter. It didn't happen. It just occurred fully formed when I showed up. But all those are little hints that Poincare was onto something. That, yeah, this point set stuff is maybe not helping us understand things. So I'm being gentle. I'm not saying it was a disease that the human race needs to be cured of, but on the other hand, it's not helping us. Maybe it's just a cough.
in the thesis story, there is no space for Brouwer?
Yes, there is.
Yeah, sure. Yeah, and you're right. I should bring that up.
Mm-hmm.
That's actually, there's another story to tell about what the open sets of a space are. You can think of them as being propositions, things that are either true or not of a point. It's true if you're in the set. And then you get something that is a Brouwerian logic, a Heyting algebra. So it does play a role in many. All right, so let's just review what space is, a point set space, the ones that Poincare was complaining about. The view is that you start from a collection of points. So your space is populated by points. Oh, mocktails, wow. Excellent. And then you specify some sort of a convergence criterion. So you say that some kind of data, maybe these are sequences or sets of points or filters. There are all kinds of ways we could specify it, but some sort of data that you want to say that data may be converging to a point. So think of sequences, right? 1/2, 3/4, 7/8, and so on converges to 1. That tells you something about the real line. And you say enough of those things, you've described the real line. And then you have this relation of convergence. So you say whatever the data you're talking about converges to X, right?
X is a point.
X is a point, and D is some sort of data that describes convergence. A sequence, a filter, a set of points, something. And you can choose, there are lots of ways we could do that. But the point is that there are basically 3 important parts to saying that this convergence is well behaved. One is that if I have a constant sequence, constant piece of data, then it should converge to that constant. That's pretty reasonable. And then you have a notion of when one piece of data is a subpart of another piece of data, like a subsequence. If I have a sequence and I pick out every other one, then if the original sequence converged to a point, then the every other one sequence should still converge to the same point. Okay, that's a pretty reasonable axiom. And I'm going to be really vague about what I mean by convergent data of convergent data. But if we iterate this process, we say we have a limit constructed of limits, then it should in some way be a limit of another thing. And it's a simple limit of another thing. And it turns out that if you write those three axioms down carefully, you get point set topology. You get a way of talking about it. There's more than one way to do it, and they all turn out to be equivalent.
Sorry, if I said that convergence only concern a final, arbitrary final segment of D, would I not tell the three in the same
Not the second. The first and the second you might be able to. Yeah.
Third, no.
But the third is more complicated because now we have to talk about what are the limits of limits. So there's an iterative thing that you have to.
But then you have the diagonal.
Then
in fact, the diagonal is not relevant because what represented
that's
the final segment of
yeah, but that's the problem is that if we only think of sequences, that's why I'm being vague. If I only do this for sequences, I don't get all nice topological spaces.
Okay.
So I have to generalize the notion of sequence, and then diagonals no longer quite make sense. We have to be a little more careful about that.
You look at these three axioms with the correct lenses, they look very much like a consequence relation. The first axiom is reflexivity. The second axiom is that whenever you expand the set of hypotheses,
It's a weakening condition.
there's a weakening condition, and the last is the cut, right?
Actually,
The cut?
the cut rule.
Cut.
Cut.
Yeah. No, you're absolutely right. I think that's something to be explored even better. And there are connections between topological spaces and logic that I think you could say in this way. I think that's a nice observation. So obviously I'm waving my hands about the details. I have to tell you what I mean by a constant data. Well, I know what that is. So, and what is a subpart? I have to talk about iterative convergence and nail all those details down. But the spirit of it is that that's what is meant by a topological space in some way. That, by the way, is not the textbook definition of a topological space. You look it up in a search engine, you'll see that a space is a set of points with a family of subsets that have a certain kind of structure, and then you can derive the convergence from those sets. But that little detail aside, this is essentially the right way to look at it. And then what is a continuous function? That's a function that preserves the notion of convergence, whatever you have. So that's analytic point set topology. So what I want to explore is this synthetic idea that what we really want to do is think of a space as consisting of these spots.
So up to now was the analytic idea.
Yes.
Now is the synthetic.
Yeah.
Okay.
Yeah. So I want to have a space consists of a set of spots. The spots should form some sort of nice structure. We're going to call these things locales. Points are a derived notion. They're going to turn out to be indecomposable. One notion of spot of a point is that it's an indecomposable subspace. So it's an atom, right? That's a pretty good reason for that. That's a natural way to think about what a point might be, is it's a smallest possible subspace, right? And continuous functions should somehow preserve the relevant structure. Now, what did Poincaré worry about? Well, this little last bit is more or less just an iteration of what I said earlier. The space consists of its atoms, so they are given to you ahead of time. Spots are a derived notion. Those are these sets that tell you how convergence happens, right? And then the atoms, if you think about it in the Cauchy sense, the atoms, the real numbers, they arise as convergences of other things, of data, right? How does Cauchy define a real number? It's that thing to which this sequence would converge if there were such a thing, right? And then an equivalence class of all of those things. So what was Poincaré worried about? He says, well, how do you build a space from atoms when atoms are nothing? They don't have any extent. They're nothing there. And just as bad, how can you build a space from things that you're going to use to build other atoms? So there's something impredicative about that situation that bothered him. So that I think is one of his main complaints, was that it looks impredicative to him. So let's look at what I mean by a spot. I mean a spot to be a thing where to the best of your ability, think of that blue thing as not being a collection of points. It's just a blob. Because I don't know what a point is yet. Okay. So spots are going to be spots. That's it. And if I have two spots, they overlap. It's really tempting to call that overlap the intersection, but it's not really an intersection. It's just an overlap because there's no points. I don't have a set of things that I can take an intersection from. But nevertheless, overlapping makes sense, right? So that's the picture.
If instead of spot, I say open set, is very different.
Yeah. What set of what? What do you mean by a set of what?
But you know, there are, I know I'm not ignorant, but I know there are formalization of topology in which the original object is not point, but is the, oh, I don't know in English. En français, on dit un ouvert.
No,
An ouvert is not necessarily a set, it's an ouvert.
No. Sure. No. And these are usually called opens in the frame theory community.
And then a point is the limit of the intersection of open.
That is where we will go. You're absolutely right. But in the first instance, we want to think about these as just being spots, right? Because points will be atomic spots, more or less. Well, not quite. That's another story. Okay, so first cut is that we expect a space to be characterized by a neat semilattice of spots, right? So spots that can be overlapped, and then the overlap is another spot. So spots are not circular, they're just spots, okay? And a homomorphism between semilattices is what you expect. It's a function that preserves the meet operation for finitely many meets. So that's where we're going to start. It's just in the category consisting of semilattices and semilattice homomorphisms. Yeah, so like I said, it's tempting to call those things intersections, but I would prefer us not to.
Only finitely many of those.
Only finitely many, so far. Okay. That's the category in which I want to think. So now, what if I have this little semilattice that I have drawn in the corner, this cube, and then I assign to each one of its elements a spot, then I get a red spot, a blue spot, and a gray spot, and then I get the intersections of those pairwise, and then I get the intersection of all three, right? So this is kind of, it's not a Venn diagram because there's nothing in them. They're just spots, and they're overlapping each other, okay? So that's an important feature of a space, is this idea that we can interact, we can talk about how the space is shaped by thinking of how the spots interact with one another. That's where we're headed on this. Okay. Now, what if I make all of those spots a little smaller? So think of this as being a way of specifying something like nested spots, one spot being inside another spot, and I have a collection of them. If I make them all a little smaller, and that says that the centerpiece, the little fattened up triangle in the middle, is, so to speak, converging faster than the previous one. So that's the way I want to think about this. Because remember, I can't think about, I'm not going to think about anything converging to a point. Instead, I'm going to compare data and say this data converges faster than this data. Not converge to something, but just converges faster. So this is an example, right? So these two functions, the second one, this one is converging faster.
What is K here? Sorry.
K was the original, this one. It's the map that sends this cube to spots.
The cube. K is the cube?
Yeah, capital K is the cube, yes.
Okay. The cube.
Yeah, thank you. Right. And H is that one, and H prime is that one. And then H prime is, in a sense, tighter, right? It's converging faster. Okay, so in a sense, if you wanted to think about limits, that's saying something like, well, H prime has fewer limits, or at least no more limits than the previous one. So that gets at the second of my axioms. It says that if I have a subpart, it will converge to more things and therefore have fewer limits. So we're going to use that as a surrogate for limits. So a little bit more detail about the category of semilattices.
Can you just as a clarification? Yep. So when you write H prime smaller or equal than H, it means that this is true pointwise? Mm-hmm. Okay, thank you.
Yeah, because semilattice homomorphisms are ordered pointwise in an obvious way.
Yes.
By that. But it turns out that that means that the set of homomorphisms from one semilattice to another semilattice is another semilattice. And composition of semilattice homomorphisms is a homomorphism in its own right. That's what this is reminding you of, or reminding me of, is that it turns out that the category of semilattices is what's called enriched over semilattices themselves. That's useful, because it means I can kind of live my life inside this category and things are kind of nice and coherent. I can talk about homs and they make sense, homomorphisms and sets of homomorphisms, and they make sense, and all the rest, right? So that's sort of a helpful observation. Now, what that means is that I can think of these nests, which I have over here. I'm going to call these things nests from now on. So this is a nest in C, K-indexed nest in C, because it's a nesting of spots. And what I want to do is suggest that a space is a space in which these nests we can use to probe the structure of the space. And if we put enough axioms on how those nests behave with one another, how they cooperate with one another, then we get a nice notion of recovering some sort of spatial information from it. And that means I'm using semilattice homomorphisms as probes, as ways of looking inside a candidate space. So I'm going to use the letter C for the thing I think is a candidate as a space. And I'll use I and J and K and things like that for the index of how I'm nesting inside. So this is the domain of my functions. So this is a reminder for those of you who don't know a lot of category theory that there's this very standard thing to do, and that is to study an object by studying its homomorphisms into that object, or the morphisms into it. And this is a very standard thing to do, and it's very regular. It's called the Yoneda functor, usually, with the proviso that now I'm in a semilattice enriched environment. So YC gives me another semilattice. So Y sub C of an index set is the set of all the ways I could use I to describe a nest. And C is the place I'm describing the nests in. That's the idea there, okay? And that thing turns out to be a nice functor. It's a covariant functor, so it turns the arrow around because the composition is on the other side. But anyway, that's just sort of a technical definition. But what it does is it allows me to say, if I want to figure out what C looks like, then what I can really do is I can step back one level and think about what its Y looks like. Namely, what are all of its nests doing? And how do they interact with one another? That's what Y allows you to do. And this is, again, that's totally standard category theory. I think you study an object by studying the homomorphism into the object. Very standard, right? And that's just the intuition. So Y sub C of I is all the nests that I could build using the index set I. H is a thing that does reindexing for me. And it allows me to inspect the semilattice C, this thing that I'm hoping is going to be a space, by virtue of how its nests behave.
So even more intuitively, the point is that you study a nest, a spot, by studying the spot that are nested in the spot.
Yeah, you can, but I'm talking about studying the entire thing by which nests sit inside it. But so that's a special case because each spot will be its own subspace. So yes. Yeah.
So in general, globally, what the intuition would be?
Yeah, the intuition is I have a space, say a torus, and in order to understand what it is structurally, I can't look locally at individual spots because that won't tell me very much.
Yeah.
But if I can tell you how spots change as I vary around, then I can start to see what the thing looks like. So it's like shining flashlights onto it, right? If I shine a flashlight on one point, one region of a torus, I might think it's flat. It just looks like it's nothing there. But if I move around and look at it from different angles and I change the nests, then I can start to detect what the structure is. And again, that is very standard way of using category theory to get at some specific area of mathematics. Right? You study objects by studying how to look at them. So that the UNITA functor also comes with an additional natural transformation. So if I have a function semilattice homomorphism from C to D, like I have pictured there, it determines a natural transformation that turns a nest, sorry about the jump there, that turns a nest that's indexed by I going into C, I map across, and that means I get a nest in D by composing these two functions. So this is a way of saying that I can compare one putative space with another putative space by transferring things across by homomorphisms. So the nests are nicely behaved with respect to this. I'm going to use that in a little while. So we need some way of talking about how fast convergence happens. And this is going to use one more bit of technology, and then I think we'll get to the more interesting stuff. So on a semilattice, I'm going to call something a filter if it is a nest in the two-element semilattice, but it's indexed by C. So that's one way of looking at a filter. For those of you who do more algebraic stuff, there's other descriptions of filters, but this is a good way of thinking about it. So script F of C is the set of nests that are indexed by C, but are only going into this really simple thing, which is the two-element gadget. And it's really easy to check some facts about that. That turns out to be, well, it's just applying Y2 gives me a contravariant functor, and it happens to have a left adjoint, which makes F into a functor. So it behaves nicely with respect to composition. So this is the filter functor. I know that sounds like a complicated way of saying it, but actually I think it's pretty nice. So don't argue with me. Anyway, the point is that this is what happens. So if I have two filters and they are compared this way, that's exactly the same thing as saying they're compared by the UNITA functor. Move to the other side. Okay. You're smiling.
No, I'm good. So this C and D, those are sets.
These are semilattices.
Right. Sets. So an F is a map between those sets.
Right.
Okay. And the filters can be characterized as
homomorphisms into two-element lattice.
And in the traditional sense, we could also characterize them, for example, as what is the set that goes to 1. So the pre-images of
Precisely.
1. Pre-images of 1. Right. So the subsets.
Exactly.
Is that F of F the direct image?
It's the direct image made into a filter. The direct image will only be down directed, but it won't be a filter.
Exactly.
So that's what this does.
It's the upset of the direct image.
Yeah. I think fitting it on one page this way is easier than doing it through sets of sets.
Right.
But it is exactly the same.
Yes.
Exactly the same.
To connect.
So remember, what was a space analytically? It was each point has a limit of its constant. That was one thing we wanted. A limit of a sequence is also the limit of any of its subsequences, and the limits of limits are limits. Again, I'm being vague about what that means. And well, we really don't have atoms right now, so I'm going to get rid of that requirement. But what I'm going to do is instead figure out what the behavior is of subnests. and see what ought to happen there, characterize that situation, characterize what it means to have a nest of nests, and figure out what ought to happen there. And that will turn out to be my definition of a locale. It's a semilattice that behaves nicely with respect to subnests and with respect to nests of nests. Exactly the thing that the analytic topologist wanted in the first place, setting aside the constants. Okay. And again, this is not, it's not exactly new, but it isn't the way that most frame theorists talk to each other about this stuff. We take something else for granted instead. I'll explain that. All right. So what about cofinality of, well, this is to talk about what it is to be a subnest. So I'm going to describe being a one semilattice being contained in another semilattice. It could just appear as a sub-semilattice. But I also want to say that anything in the bigger one has something below it in the other one. If you think about sequences, what would be a subsequence? It would be picking out maybe only the prime numbered ones out of it. Well, that says that anything in the subsequence has something further along in the, no, sorry, anything in the main sequence has something further along in the subsequence. And that's just capturing that idea, this subnest idea, all right?
And just for further along, you mean smaller?
Smaller.
Yeah, which is
right, because we're converging towards something.
Yeah.
This is what we want to think about. So smaller means we're converging towards something. This is the accumulation of information. So I'll say that again, C, which is my putative space, I'll ask for it to respect subnests if it has this property. And what it says is essentially, if I have two nests where if I'm comparing two nests, G and H, that have the same index set, then if J thinks that one of them converges faster than the other one, then it does converge faster than the other, as long as I and J are in this subnest relationship. And that's a pretty faithful translation of the convergence of subsequences is respected. This is almost a literal retranslation of that axiom from analytic topology, but just in this language. Subnests behave nicely in this way.
Can you help me understand what you mean by J thinks G converges?
Yeah. So I've got J is this, so J is this lens, and K is, so J is a flashlight, and K is how I am flashing it into C. All right. So I can move K around and I can look around, but J is the lens I'm using, so it's not changing. Right. So now if J says, well, look, every time I think, so H is below K restricted to I. So it's sort of like I've taken whatever this lens J says and I've removed stuff from it. So I'm only looking at the I part of it. If that says this one's converging faster than the other one, G is converging faster than H, then indeed G is really converging faster than H.
Okay, so by thinks you really mean as seen
Can
through the light.
Can see it. Yeah, can see that. Right. That would be a better way of putting it. Yeah, J can see that G converges faster than H, then G does indeed converge faster than H. And again, that's a pretty literal translation of the subsequence or subdata or subfilter property from analytic topology, just into this kind of strange language. All right. So that's going to be one of my criteria for being a space, is that it should be a semilattice that respects subnests. Now, what about iterated nests? Well, that's pretty easy because I get this Y thing. So if I have a K that is shining itself into the nests, into the J nests, that's an iteration of nests. That's a nest of nests. That's exactly what it is, right? And well, what's the behavior you would like to have? Well, you'd like to have that expression there. So for any such n that's sitting up at the top, there's a maximal f that that makes this little filter over here work out. I don't have a good picture for that because it's kind of a four-dimensional thing that's happening here. But again, that's pretty near to a translation of what knowing that there is a diagonal in a nest of nests. That's the maximum F is one of the diagonals that I could have had, one of the subdiagonals. And now I'm saying there's always going to be a biggest one. Okay. So again, this is more or less translating the idea that sequences of sequences will converge to, if they converge, then the diagonal will also converge to the same place. It's pretty close to the same statement. Okay. So I'm going to call that an I limit. So this maximum F is the iterated limit. Not a limit, but it's something like a limit. Okay. What happened? It's not moving. I'm not moving.
You reach the limit.
I reached the limit.
The battery.
I have another one.
Off and on again.
On your computer, make sure that it is.
Yeah. So can I do it
You
here?
do the arrow keys, yeah, the arrow keys should work.
No, that's not.
That's not it.
That's not here.
There we go.
Okay. So it just came back alive. Okay. All right. Thank you. Thank you. Good thing I wasn't chewing gum at the same time.
Jose, go beyond the limit.
I will.
Yes. Yes. All right. So see, having iterated limits means that these nests of nests behave properly, meaning I can find a thing that gives me a diagonal to navigate through the nest of nests. And I can do so in a canonical way as a maximum. Well, so yeah, this is kind of my attempt at a picture like this. So I have this nest of nests, and that means that for each J, I have a nest from K, and that means that, well, this is just kind of useless. There's a maximum one that makes all of these things true for all J's. That's a bad attempt at animating the first order sentence. Okay. Now, it turns out that this iterated limit idea already is recognizable in other ways. So this is something that Anna and I just figured out in the last couple of weeks, is that these are equivalent statements. The semi-lattice itself is complete, has all meets, is equivalent to having iterated limits. And these other ones are also case. And also every Yoneda J sub C, all of those are also complete lattices. And all of those things are equivalent to the Yoneda functor at H having an adjoint, having a left adjoint. So these are equivalent statements. The one that everybody would have been using all along is that C is complete. Right. But it turns out they're all the same. So if I have that condition, if I have any of those satisfied, then I'm going to call this right adjoint that exists, I'll call that L of H. And it's really easy, just for category theoretic reasons, to see that that's a functor. That's always going to be a functor. And notice that this adjunction relationship, this should look familiar because it's exactly the same thing as F and Y2. So that makes sense because 2, you would expect that to be a space. It's the space that has nothing, it's the trivial one. It's going to wind up being the point. So what we're really doing here is saying that a space generalizes the notion of filters in the sense that there is an adjoint to the Yoneda functor. That's what filters got me for 2. Now I'm saying, yeah, I want it true for these other guys as well. Okay. And so now we have it. So a locale is going to be an object that distinguishes subnests. So it behaves nicely with respect to subnests, subsequences, whatever you say. And it has iterated limits. So it behaves nicely with respect to nests of nests. And those were the 2 criteria we want. And now here's another nice little theorem, which says that any semi-lattice that meets those 2 conditions is complete, and this left adjoint to the Yoneda functor preserves monomorphisms. And that is the same thing as being complete and satisfying this infinite distributive law. And that's the one that everybody will tell you is what we mean by a locale. This is usually the official definition of what a locale is, a frame. Again, those are synonyms. But what I'm pointing out is that this is a consequence of thinking carefully about how convergence ought to work. Sub-objects, subsequences, and iteration. If you're working with these things, this is the one you want, because this one you can calculate. The other thing is just pretty abstract.
In the previous theorem, when you mentioned that those properties that are equivalent to being complete, you said complete is it has all means.
Mm-hmm.
I wasn't expecting that because I was thinking about that. I was expecting that it has all joints. Of course, it's equivalent.
It is.
But how did you think of it? When you proved that those equivalencies, did you prove that it has all joints, or did you did you prove that it has all means?
That's a good question. I think the first thing I noticed was that every CYJ is complete as meets.
As meets. Okay.
And then I said, oh, well, that means that C is complete because for a really easy technical reason that I don't want to bother you with.
Mm-hmm.
And then I know that joins are going to work. Yeah, I'm pretty sure I knew it from the meet direction. So now what is a continuous function? Well, a continuous function should preserve limits. Well, we now have two things to think about preserving because we don't have limits. We have these iterated nest things. Those should get preserved. But we also should preserve something having to do with subnests. And that one is a little more awkward, but basically what it says is that the filter functor applied to F is a neat semi-lattice homomorphism. Remember, it's a right adjoint, or sorry, a left adjoint. So it's not required to preserve meets. That's just a general fact about categories, functors on categories. So if I insist that it preserves meets, then what I'm doing is telling you that this thing behaves well with respect to subnests, because I characterize subnests in terms of the behavior of filters first. All right. So that's what I'm going to call a locale map, which is the analog of a continuous function. It has those properties. Let's see, how much time do I have?
Let's see, 1 hour.
Okay.
So
Okay. Yeah, I've got plenty of time. I just didn't know if I wanted to go through these details because the details are, they don't always give you the lay of the land when you talk about little things going on. But what is a localic map? Well, I had this really, that's a pretty abstract definition of what a localic map is. It preserves these things, fine, but you'd really rather have a definition that you can calculate. So here's a characterization of what they have. So a localic map preserves all meets, and has this boundedness property, which is basically saying that it's saying that the filters are preserved under meets. That's a translation of that fact. Some of you who know a little bit of modal logic will recognize that I use the word bounded because this looks like a bounded morphism in modal logic. It's got a similar formal structure anyway. Another characterization is that it preserves all the meets, and the Yoneda functor applied to the adjoint of F is a natural transformation. Oh, that should be an L sitting right there. It's a natural transformation on the L functors. Remember, YF is always natural, but now I've got I'm saying that Y of the adjoint is natural with respect to the adjoint functor, the morphism-wise adjoint functor. And the other one is that F preserves all the meets, and F star is a meet semi-lattice homomorphism. Being a left adjoint, F star preserves all joins. So F star is what we call a frame homomorphism. So in other words, a localic map is the adjoint of a frame homomorphism. That's, those of you who know more frame theory, that's really what that says. So now I have a nice kind of abstract characterization. of what a locale map is. I have a few ways I can calculate with it. And the last one is the one you really use because it tells me exactly what's happening in the opposite direction. It tells me, if you want to think of it this way, it tells me what the inverse image of my localic map does, how it behaves. And in topology, inverse images are pretty important. So that's what that gets me. What is a sublocale? A sublocale is just going to be a sublattice, semi-lattice that is a locale, has these properties. And the inclusion map is one of these localic maps. In other words, it's a sub thing just exactly whether we want it to be a sub thing, just like a subgroup or a subring. It's just exactly analogous definition. So that's what I mean by a sublocale. Now it turns out that the SL, the collection of all of them, is kind of nice. It's really easy to check that it's closed under all intersections. So it's a complete lattice. It's also easy to check that it has lots of other structure that I'm not going to go into right now, but it turns out that it's not another locale. It's upside down from what it should be. If it were a locale, it is a locale if you order it in the wrong way. Kind of weird. And there's lots not known about it. There are a lot of things that are known. So that gets me to points now. Okay. So what is a point in this synthetic view? Point is going to be an atomic subspace. Seems like a very natural definition for what a point is. So it's a sublocale, in other words, a subspace, right? That has it cannot be reduced until it's reduced to nothing. If you try to reduce it to something smaller, you've reduced it to the empty sublocale. So it's atomic in that sense. It cannot be decomposed any farther.
Is it a null element of a set?
Well, it's an element of a set of points, but so what?
No, I mean, the intuition is the same. A point is a set that does not subset.
Yeah, yes, that's right. Yeah. I mean, that's what you should, that seems like that's almost the only thing you could want to, well, no, there are going to be two others. One doesn't work very well, and the other one that works just fine. Yeah.
Do you have room here for the empty locale? Or
Yes.
not the empty, but
Yes, what is the empty locale? It's the singleton semi-lattice.
Singleton semi-lattice, yeah.
Right.
So, and it contains a sublocale that is irreducible?
No, it doesn't. No, it has no proper sublocale.
It has to be proper. Okay.
Right. Good. These are bounded. I didn't say this, but my semi-lattices always have a top element.
Yeah.
So this is that's the thing. So the singleton semi-lattice is the zero object in the category. There's a unique function into it, and there's a unique function out of it.
Yeah.
So it annihilates everything, right? So it really behaves like zero should be.
Right. But when you define a point, it has to be a proper sublocale.
Trivial. Yeah.
Oh, I should have said that. Yeah, you're right. It should be proper and not have trivial sublocales. Yes. Right. So its picture is a two-element set. And if you want to go through the exercise, it's not hard. You can assemble all the points and then put a topology on those points. So you can get a proper analytic point set topology from that process. That's always possible to do. Localic functions, these localic morphisms that I was talking about, they preserve points in a trivial way because if I just compose a point with a continuous function, I get a point. So that's the proof that this thing is continuous in the right way. It sends points to points.
True. How do you prove that there exists something as a proper sublocale that has not non-trivial sublocale? Because how do you prove a point exists?
It might not.
Might not. And I'll show you an example where they don't.
Okay.
Yeah, Jonathan.
You get a functor of points somehow from locales to.
That's that point.
Yeah, PT is a functor.
Does that have is that part of an adjunction?
Yeah,
Yes.
it's an adjunction between lock
And
A dual adjunction between lock and topological spaces.
Okay, so it has a left and a right adjunct. Yeah. Yeah, I mean that's
Yeah. The other direction is almost obvious. It's that you take a topological space and you take the lattice of its opens. That's a locale. That's the one direction. This is the adjoint. Okay. But there are these spaces that have absolutely no points in them. So let me give you let me take a little time to get this one. So I'm going to call omega r. That's the one I just mentioned. I take the real line that we're all familiar with, and I take the open sets of that line. So what is an open set in the reals? It's a union of open intervals. Right? It doesn't have to be an open interval because I can have a chunk here and a chunk here and a chunk here. Like unions of open intervals, that forms a locale. This is the locale of the reals. That's one way of seeing it. Okay. Now I can define two other locales. I'm going to call this one omega q. And what it is it consists of all of the open the open sets of reals that have the property that any other open set of reals that agrees with you when it comes to the rational numbers, then it's in U. So what's an example of a set that isn't open? That's the one you really want to think about. That's open in the reals, but it's not open in Q. Why? Because Q can't see this hole. It doesn't know it exists. For Q, it simply doesn't exist. Right? So this is not an open in omega Q, but it is an open in omega R. Now, you have to do a little bit of thinking.
What is it in Q?
It's just nothing. It's not an open set. This is open. And it doesn't matter what the endpoints are. They can even be irrational endpoints. That's fine. But
I'm not understanding which sense is not open. Is open simply is not.
No, I'm just telling you which things I'm going to call open. And what I'm saying is that it isn't open because Q cannot tell it from. It cannot make the distinction. Q
okay.
Cannot, right?
It's clear.
And that's what I mean. So that's what that's telling me.
It's the second.
So in a Q, in Q, the open that you are drawing there and the other two open are the same thing.
Right. So they are the same thing. That's what my definition guarantees. By saying that the smaller one.
What does it mean that they are not open?
The smaller one simply, no, the smaller one simply doesn't even exist. I need to tell you about a set of spots. That's not a spot. This is not a spot in Q.
The confusion is that he's trying to define the topology as of Q as the restricted topology.
I know.
You are defining locale.
I'm defining a locale. I'm telling you what the spots are. Right. It comes to the same thing. But that's analysis. You have to sit there and think about what that means. So what I'm describing are the opens of Q in just the way you are. But I'm trying to describe it directly as a locale. Now I can do the same thing for the irrationals.
So it might look like the same thing, and probably this is something that is isomorphic.
Yeah.
But it's not exactly the same thing because by definition, your opens of the locale that you're defining on Q, they contain irrational numbers.
they do. They
Oh no, that's a very good point. So they aren't identical. They are isomorphic.
They're isomorphic.
They're isomorphic. Very good point. Yeah, you're absolutely right. Okay. Well, so now I can do the same.
Subspace of Q. That's.
It's not a subspace,
No,
but it is isomorphic to a
to the
subspace.
subspace. Yeah.
And I can do the same thing for irrationals. That's what the second line does. Right. Now, the points of omega Q, well, they do correspond to rational numbers. And again, a little bit of, third year analysis you can prove that. And likewise for the Q of R minus Q, that's the irrationals. Okay. Both of those are dense in R. There's a technical meaning for dense in locale theory, but that's it, and it's correct, right? But here's the thing. Any two dense sublocales, if we intersect them, it's still a dense sublocale. Now, in point set topology, that's completely pathological because Q intersect irrationals is empty. But here it's far, far, far from being empty. It has no points because I eliminated all of them. That's a weird thing. It's a really weird thing. So an important theorem this is like a milestone in locale theory, is that every locale has a smallest dense sublocale. And if C did not have any isolated points, then the result has no points. That's a fact. So you can always sort of vacuum out the space and remove all the points. And you get something which is still quite large, but it has nothing in it.
But Drew, you can vacuum out all the points, but you don't get down to.
You don't get down to this, and we're going to come to that one. Yeah, that's exactly right. So, but you can see that there's really nice natural sense of in which there can be points.
Sorry. Intuitively speaking, is something that I do not understand. So the locale is not made of point.
No.
This is the first basic idea, because otherwise, all what you said,
you're tracking. You're just doing it fine. Okay.
And now you say you construct me something that is a locale and there's no point inside, and you say empty. It's not strange, because this idea that something that does not point is empty.
Oh yeah,
seems to justify the idea that is made of point.
Exactly. It should bother you.
Strange.
This absolutely should bother you.
That's what's wonderful.
Yeah. So we're saying that if you think that a space is empty just because it has no atoms, you're wrong. It is not empty. You can have very highly structured spaces that nevertheless have no atomic parts.
Okay, but this is empty. So this is empty or not empty? Then?
No, it's not empty. It simply has no points.
So why you wrote empty?
Because he
I put it in quotes.
Okay. Now you use a quote as a negation. Okay. Not in there.
No, it's ironic.
Mathematician.
It's ironic.
Okay. Go ahead.
Yeah. That's the ironic.
Potential is inside the contrary. It is Marco without potential means the contrary. Okay, Marco potential is
a really nice guy.
That's how you really think, Drew.
I'm channeling Poincaré. So this pointlessness, Rick Ball has recently really done a nice job of thinking about, well, what happens if we do this the least we can do, which is just remove all the points. And there's a nice process for doing that. He doesn't like this term, but I think the results should be called vacuums. So if I take a space, again, one of my synthetic locales, I can find the largest dense subspace that has no points. I can find the largest space that has no points, subspace that has no points, and it's going to be dense. I think I just said that wrong, but you get the basic idea. So but he only proved this for completely regular spaces. And if you thought about that, whether this is also true in general.
He doesn't do it for completely regular, does he?
Yeah, it's Rick. But
the stuff doesn't depend on.
I don't think it does, but I think that needs to be checked. So I'm stating it carefully as his theorem, which says that this is the fact for completely regular spaces.
Drew, I've got an idea what dense means for, rationals, and so what does it mean when there are no points left? In what sense is it dense?
Its closure is the whole thing.
Okay.
That's what you mean by dense. That's why Q is dense in R.
Okay.
Is that if I take the closure of the set Q, then it captures all the irrationals.
I see. Okay.
So dense means closure is the whole space.
Thank you.
Yeah, thanks for stopping me because I took that for granted. So his result is that for at least for completely regular, but we believe it's probably a more general theorem, the C is always obtained uniquely as a subdirect product of its pointed part and its vacuumed out part. So it's a subspace of the direct product of the product in which both of the maps are onto. That's what he means by subdirect product. So it's a pretty interesting canonical way of splitting a space into the pointed part, and then all the action that's going on in the unpointed part is separate from it. And he does a really nice investigation of how this stuff works. But again, he throughout assumes complete regularity, and I don't think he needs to, but I think that's something that we need to check. So that's a pretty nice way of thinking about what points are. Atomic subspaces. And with Rick's result, it tells you that a space factors into its points and whatever is going on in the vacuum. And they're separate. He even goes a little bit farther by saying that if you replace finitely many points, there's a systematic way of doing it. So there's a lot to investigate. This is fairly new result, so there's a lot to do here. So here's another view of what a point might be. Remember, I have this semi-lattice of spots, and they're in lattice. So now this is a complete lattice. So there's a very common notion of an atom in a complete lattice. It's a point that's at the very bottom of the lattice that's just above the bottom. So it's something that can't be reduced without reducing to the bottom. That's a standard definition of what an atom is in a lattice. So I could take, well, maybe those are my points. They're simply atomic spots rather than atomic subspaces.
For example, if you take the locale of the reals, there's nothing like an atom.
Right, there won't be any atoms here. Right. So this looks like it might be a nice definition, but this one we're going to throw out. It's not so nice because it turns out that this simply means, I mean, actually, Rick also proves some things in that same paper about what happens here. If you take the closure of a vacuum, you get something that has no particles. So there are some things to talk about, but it turns out that particles aren't very interesting because what they are isolated points. They're the same thing as isolated points. Mm-hmm. So they're not really very interesting as atoms. But it is an alternative. We could think of it this way, right? And, you know, like I said, there's some theorems there. But now here's the third way of thinking about what a point is. It's a location. So when I constructed the locale of the rationals, I referred to R as I was doing it. So what role is R playing? R is playing a role of being sort of like the coordinates from which I assemble these spots. But the coordinates don't have to be spots themselves. So I could think of that as saying, well, so yeah, okay, so what did Descartes do for us? He said a point in the plane is the same thing as its coordinate, as a coordinates, right? So, but that's conflating two different ideas. There's a location, which is the pair of the XY pair that's telling me where the thing is, but there's the point. And before Descartes, the point was it, right? That's the one we cared about. Now we say, well, they're really the same thing. Well, so this result, which is really quite new, we haven't read submitted the paper yet. We haven't tried it. It turns out that every locale can be embedded into a kind of nicely behaved spatial locale. In other words, one that's built from this analytic point set point of view. And I didn't change this. That's a subfit means Wallman separate. So it's a sort of a nicely behaved actual concrete space with atoms, with points. And every locale can be so embedded. So what that means is that I can take a space, one of my locales that has no points, So I just find it some abstract way. And now I can supply coordinates that tell me how it came about, or a way to make it come about. I can say this is somehow a dense subspace of a concrete analytic space. So this is a different view of what a point is it's not a thing in the space, it's a location. It's a way of describing something, how to find your way around in the space. And those are very different. Because we're supplying extra points that don't exist in the original locale in order to give ourselves enough landmarks to tell where we are in the locale. So they are locations, and that's it, right? And like I said, this is a paper that we're just writing now. So there's just a ton of questions that I still have about this. One of them is this really a canonical? I think the construction that we have is probably not canonical in any way. We just say, yeah, we can build enough points to make you happy. But I don't know that it's minimal. I don't know that if there's some kind of saturated way to do it. None of that. We don't have any idea about any of that stuff.
Question, Drew.
Yeah.
So in a vacuum locale where there are no points, do you have a way of, how do you talk about where the spots are?
Well, that's what we're hoping. At least I'm hoping. I haven't talked to Joanne and Alish about this, but what I'm hoping to do, because this just came up. This really came up from last week's talk. I started to think about this. What I would like to do is say, yeah, that thing doesn't have any atoms, doesn't have any of these smallest subparts. But what I can do by this process is I can sort of project it onto a coordinate system. So that adding all the points will tell me how to navigate through it, right? Those locations won't correspond to atoms in the original space because they can't, because the thing had no atoms. But they will correspond to ways of describing the behavior in the space. So
in your vacuum locale, you'll be able to that things just represent themselves. Like you'll have these opens, which are just characterized. How do you characterize where they are, and do you need to remember the points in order to forget them first? Like, is there a way that you can still talk about it?
We are perfectly happy talking about locales that have no points. That's been that's totally fine. That's not pathological from our point of view. But this is a nice result because it says that you can coordinatize even a point-free locale. You can supply it with a way of thinking about locations. What you're not going to be able to do is say that, oh, in that case, these locations are the same things as points. They just aren't. And I think that's one of the values of locale theory is that it separates these two concerns, right? Understanding what a point is as a piece of the space is different than thinking of a point as a location. It's exactly what Descartes conflated, we're deconflating.
So if we're thinking of just the coordinates of something, and we can specify the coordinates so that we can sort of pin down the location to arbitrary precision, we can make that location as small as we want.
Right.
I mean, we're getting a lot of the same sort of conceptual, pieces of a point. So, I mean, I guess I kind of know what's missing from the way you developed this, but can you just switch over and use like this new picture where I have locations and no points? Will it make any difference to a lot of like physics, for example?
Oh, I don't know. Okay. I mean, my intuition is that physicists tend to use stronger mathematics than they need. They tend to sort of buy things off the shelf.
Yeah, that's exactly what I was going to say.
And I think this is
available. Yeah.
And this is not buying it off the shelf.
Okay.
Right. So again, if you think a conceptual difference between saying I have a piece of the space that's atomic versus I can tell you where you are. If you think those are different things, then I've got something for you.
I mean, maybe you kind of had a hint of this. Maybe the point is really the thing we tend to think of as a particle in physics.
Right.
And the location is sort of the background in which the particle might live. Yeah.
And this is saying you don't have to make them the same. Right? We don't have to follow the last 300 years.
Does it give us a way to talk about like the location of a hole in a space?
Well, I mean, there are ways of talking about holes anyway from algebraic topology. That's kind of what that was for in a certain way. This fundamental group is a way of detecting holes. So I think that's already there. So I guess I don't know what to say about that.
Okay, I guess, can you have a location that is not a point?
Yeah, for sure.
Okay.
Yeah.
I think that answers the question.
In fact, in the example where I had omega q intersect omega irrationals, that was a locale that has absolutely no points. But if you write down what the subsets are, starting from the reals, there's still sets of reals. But the reals are now only being used as locations. They're not being used as points anymore.
So you have all the same coordinates you had before.
You have the same coordinates, but you don't have the same space. Right?
That's really nice.
That's a different picture. Yeah. And I got to thank you, Luke, and everybody who was asking Chip last week these questions, because I wasn't thinking about it this way. But I think this is a really interesting separation of concern. Points versus locations is something I've never really thought of being different. But this result, coupled with the other things, I think it does say that maybe they really are different. So stay tuned. I think that's going to be something we'll do later. Yeah, let me just do a couple of other things just to talk about what I'm interested in talking about soon. This is just to remind myself that the category of locales has products. You don't need to worry about how they get built, but there is a notion of product in the category of locales. That's the right notion. It's the category theoretic notion of a product. And you can build it this way. I think there's more to say about that. They're notoriously kind of difficult to think about, even for frame theorists. Finite products are kind of okay, but infinite products are just weird. It's just a hard thing to think about. Anyway, but now, once you have products, now you can start talking about algebra on a space. So just like we have topological groups, we have localic group. And a localic group has a very natural definition. It's a locale with operations that satisfy the group equation. But now the question that comes to my mind is, what happens when I remove all the points from a topological group or a localic group? Well, I can't remove them all because the neutral element is a point.
You can, but they cannot get with them.
Yeah. So this raises a question. What happens if I take all points out of a localic group? What am I left with? But let's start a little more gently and say, let's remove all the points except E. So if I have a localic group, then it turns out, this is a little lemma that I worked out in the last couple of days. Their product is a point. The product of two spots is a point, if and only if both of them were points in the first place. And likewise for inversion. So what that means is that whatever this localic group is doing is it's moving points to points in a group fashion, and it's moving the non-pointed part also in a group fashion, except that it's avoiding the neutral element. Everything away from the neutral point. So what that tells you is that the pointed part is again a localic group. And well, no, I've actually misstated the last part. It's not true that vacuuming out will leave us with a group, because that would mean that A times negative A would wind up having to be E. And that would mean that both of them would have to have been points. So I misstated the last part. I was too fast about that. But the first part is true. That the pointed part of a localic group will still be a group. That's definitely the case. And there is something interesting to be said about this part. Now, I think, did I say that? No, I didn't put it in there. There is another result, which is that if I put the groups, if I lift the group structure by way of the filter monad, so instead I think about the filters instead of the original space, then I will get a group.
Drew, why did you think of addressing locality groups, like with the points, and why would that make sense? I don't know. I didn't mean it in a mean way. It's just I'm trying to think, why would thinking of the vacuum and the points would lead you to think of those two things also in locality groups, which are quite complicated.
No, that's fair enough. I think my short answer is I just thought it might be interesting.
Okay.
I don't think I had it.
Maybe it could give you like some tools that you're trying to find in groups.
Yeah, I would like to know what's happening in the vacuums, because we just think about spaces. I think so much about even locale theory. I still think about it as, well, these are just kind of like spaces.
Right.
It's really easy to do that. But there is this whole adjunct piece. There's the chunk out there.
It's so big.
It's really huge.
Mm-hmm.
The non-spatial part of this thing is very, very big.
Substantial.
But we don't really know anything about its behavior.
Okay.
So looking for structures where we do know a lot, because there's a lot of literature on localic groups. They're very nicely behaved. There's lots of nice theorems about them. Subgroups are always closed, for example. That's a very nice fact, which you don't get in topological group theory. Okay, so lots of really good theorems that are well known. So I thought, well, this is a place to go looking for what structure is going on in the vacuums.
Okay.
Yes. That's the reason.
I see easier places.
You know, it's the usual kind of inside baseball.
Okay.
So there's
question.
Go ahead, Luke.
Go ahead, Luke.
Okay. So these groups would be, if you suck out all the points, or don't forget about sucking out the points.
Right.
You can have these spots, and every spot has a notion of inverse, and then you can get spots from spots in this way.
Yep.
So I can take any Lie group and construct a localic Lie group or something?
I would guess so, but Lie groups already have some topological information built in. So I don't know how that
You have productive points.
Right.
Or additional points, right?
Right, but you could lift that to the localic setting.
So for example, U1, just the circle group.
Right.
Can I think about how I'm very curious what it would mean to be taking spots on the circle group and composing them in this way. That's a neat idea.
Concretely, that one's easy. You take the circle group. Now you take an open set will be a union of open arcs on the circle, right? And now if I'm going to add these two, I just do it pointwise. I just add everything in this segment plus everything in this segment, and that moves me somewhere else.
So it's like the group of arcs.
Continuous. And that's a continuous, yeah, right. You just add arcs in the obvious way.
Wow, that's very, very cool.
And that's a continuous function. So that's easy. That's very well known. That's actually classical topological group theory that works there. But what we don't know is what's happening with these weird, mysterious sub-objects that aren't spaces. These point-free chunks of it, we don't know what's happening. So
I can almost get some intuition for what the vacuum would be. If you suck out all the points, then it's almost like the physicist's problem of approximation. You can never be certain that you can get pinned down the point, but you can always make it as small as you want.
Yeah. And I think that's really where this group theory I think should go, is that I actually remove E as well. And what I do is I replace it by a prime filter of opens. And then you think about how filters interact with one another. But it's very early, so I don't know how that's going to shape up.
So So I was going to make one more comment.
Uh-huh.
You go back to the last slide too. So just carrying this idea that points correspond to particles in physics and the rest are vacuums, the fact that you have this product defined so that if you multiply a spot by a point, it kills the point. That sounds kind of like an annihilation. And you have inverses of spots. Do you have anything that's going to be like an analog of a creation?
I don't know.
Okay, we can leave that for later.
Yeah, something we can talk about. Yeah. Look, I think locale theory has something to say to the rest of mathematics and physics. It's just we don't know what it is yet. I really do believe that. There is something I kind of have to agree with Poincaré that there's something a little bit unnatural about spaces and thinking about points in this way as the space being constructed from the points. That seems a little odd to me. So, but I don't have applications yet. I think the applications will come up once we understand better differentiation and integration. Because this is not geometry yet. This is just topology.
This exactly was my question.
Yeah.
Okay, you answered my question before that.
And I'm not alone. I'm not alone in saying that needs to happen in order for us to be useful.
Some has been done.
Theory of integration has been pretty nicely worked out.
Yeah. Differentiation.
Differentiation, not at all. People have attempted it and it's always awkward and it just hasn't worked.
Because differentiation is essentially a local fact.
Exactly.
So it's very difficult
so it's really hard to see
differentiation without point.
Yeah, especially if you don't have uniformity, because it could go really wild very locally. Yeah.
I mean, there's measure theory for topuses due to Labier.
So
is that
Here we go.
connected? Yeah, okay.
Yeah. So measure theory is an important thing going on here. So this is something from Alex Simpson about what, 10 years ago, something, maybe 15 years ago. Okay, so he defines, well, he didn't define, but he borrowed a notion of saying what is a measure on a locale. So you take all the spots and you assign a real number, a positive real number to each spot. And it has to satisfy some obvious axioms that make it look like a measure as you would expect from measure theory. Meets and joins behave nicely and blah, blah, all that stuff, right? Now, if the measure is finite, he proves that, well, you can take the intersection of all of the sublocales that have that same measure as their weight. So you take a sublocale, and if it is assigned the same m, same total measure, then we keep it, we intersect all of those, then just almost automatically, that thing will still have the same measure. So what you wind up with is a space, a subspace, that's the smallest one you could have had that has retained the full measure. So you've not lost anything measured theoretically. You do that. It's not at all hard to show that the resulting space, the resulting locale is dense, because if removing isolated points won't change the measure, right? So you can remove isolated points. Those are gonna go away in this process. But you will retain everything else, except the points, it turns out. So Alex shows that there's a really nice technical meaning to saying that the resulting space is, so to speak, the totally random part of your original locale. What he means by that is, roughly speaking, every law of probability that would hold in C still holds in R. And because once you have a point, any point can't be random, because I can say it's that point. So what he's doing is he's saying this is the space in which you really could be doing probability theory on this, or measure theory on this object. It's pretty clever stuff. I'm not giving you any of the technicalities because it's pretty complicated. But it is really beautiful. And the thing is, like I said, no matter what, this random sublocale is always point free. And again, if you remember back to your probability theory courses, that kind of makes sense, because you never talk about a point, you talk about events, which are these fat things, they're spots, right? So you're measuring the events.
Well, yeah, discrete. Well, there's discrete probability and there's continuous probability and continuous probability.
Well, in discrete probability, you're using the topology in which every point is isolated. So,
Yes.
so that's a special case. You're absolutely right. But the general case is you have continuous data, and then you are never considering what's happening at an individual real number. You're always considering intervals, or more generally, spots. Those are your events. So what Alex has done is he said, well, if you do this classically, then you have to do all of the stuff you do in probability theory about, well, saying, oh, we're going to ignore null spaces and all that stuff. And he's saying, no, actually, there's this perfectly reasonable, well-behaved subspace that is the random part of your original. You just have to give up on the notion that points are something you cared about in the first place. Quite nice. But there's almost nothing known about it. He wrote this paper about 15 years ago, and he never wrote another thing about it, and nobody else has either.
Well,
Is that right?
Raquel's she's almost done. George's PhD student.
Oh.
Her thesis is on Moshier.
Oh, excellent. Oh, I'm looking forward to that.
Yeah.
Yeah, because we need to, I think this is really good. This is really a nice piece of locale theory, applied locale theory, so to speak. And again, this is what's going to make it useful to other people, is if we can really convince people that this is a way to do probability theory. That would be an advance.
Your last one, let's see.
And the last thing is important too, right? Because it's point free, that means it's bigger than the vacuum. Right?
Smaller.
Vaccine.
Smaller.
Smaller.
Smaller. Yeah. Sorry. I said it wrong. I said it wrong.
Yeah.
Yeah, it's small. But it's still bigger than the Booleanization. So it's sitting in this funny little interval that we don't know very much about. So that's pretty nice. Let me go back a little bit. Was that what I wanted to say? Well, yeah, so another couple of things, and then we can finish up here. I mentioned this C of a space. This is the set of all sublocales. It turns out that that's not a locale if it's ordered by containment. If it's ordered by reverse containment, it's a locale, but that's the geometrically wrong way to think about it. That's wrong. Those are no longer subspaces, those are superspaces. That's weird. But if you do it twice, you get a locale, and you get it in the right direction. And there's some known about that. It's really a nice structure. It has, as it were, the same points as the original space C, but it is really very much like the discretization of the original space. So you're sort of forgetting how things are attached to each other. Nevertheless, there is still this huge vacuum part of it. There's still this completely pointless part that is that's growing as you iterate this S functor. Keeps getting bigger and bigger and bigger. And in fact, it's known that there is not even an ordinal limit for how far that can go. You could have to reiterate this infinitely often and you'll get something new. But like I said, there's a lot there, a lot to talk about. You can think of it as being something kind of like almost the discrete space that corresponds to S. Because its points do give you the discrete space, but now you have this extra stuff that's floating around it. And there's a lot of things that I really want to look at this summer to think about how this works. And we really think I think we need to understand how this can be used to generate locales. And that comes me to, this is kind of the last thing I wanted to bring up, the last technical thing. And that is something that Poincaré didn't concern himself with, but probably could have. And that is that homotopy theory, which again, remember, he was kind of the person who started building it in the first place. If it's living on point set topology, then topologies, even completely regular, very nice looking spaces, don't form a Cartesian closed category. So that means that what you don't have is well-behaved spaces of functions on spaces. That's what it means to not be Cartesian closed, roughly speaking. Well, unfortunately, the same thing is true for locales. So locales also don't form a nice Cartesian closed category. But what the point set folks have done, the homotopy theory people have done, is said, well, we can build a Cartesian closed category by a process called compact generation. And what you do is you say, look, I'm going to take a space X, and I'm going to forget it's a space for a little. And I'm going to tell you what its continuous functions are. The functions from my space X into some other space Y. The functions that I'm going to call continuous are the ones that are continuous when they are composed with a nice function, namely a function from a compact regular space. Compact regular, like the unit interval. In fact, you can use the unit interval as the only one if you want. That's good enough. So that's what it means to be compactly generated, roughly speaking. And it turns out that the compactly generated spaces form a Cartesian closed category. So that's what homotopy theory people have done for quite a long time, 40 years. Ahmed, do you know when Kelly thought about compactly generated spaces? It's got to be more than that. 1960s maybe?
Must be something like that, 50s or 60s.
Yeah. So anyway, that's pretty well understood how that process works in spaces. We don't know how it works at all in locales. So this is something that Anna and I are working on, trying to understand how it works. And I think that this S squared is the surrogate for discretization, which is what we need in order to describe general non-continuous functions. So I think this is where we're going to go. We'll see. Stay tuned on that. Anyway, just to summarize, what I tried to set out is the idea that we can think about a space synthetically by thinking about what is the behavior of convergence, not convergence to something, but just what is the nature of convergence. And retaining the two things, convergence in terms of subparts should be well behaved, and with respect to iteration, it should be well behaved. And if we capture those two things carefully, then we actually reconstruct the theory of locales, which are, again, frames and all the rest. This also gave me this way of saying we have more than one way to think about an atom. An atom is a point in the frame theoretic sense, or an atom is a location because we can now supply it with a spatial thing around it, or an atom is an isolated point. The middle one is the one that's not so interesting, right? And a bunch of other stuff that I didn't try to put on the page. So anyway, thanks for your attention.
Okay. Any questions? As many do it.
Yeah, I like it better that way anyway.
Yes.
I like being interrupted. That's good.
I have a question.
Yeah.
Thoughts on the question?
Some.
Go ahead, look.
Okay. I'm trying to think about what it would mean to define functions over these spaces. And for example, the kind of function that would be, you give it a spot and it spits out a number, but in such a way that when you refine to spots within the spot, it does so in a consistent manner. And then you can get all the way down to points, so that there's sort of like this multi-resolution definition of a function. Is this something that you can do?
Yeah, so right. So I think what you want to say is that your function is going to take a spot and it will spit out a spot of reals.
A spot of reals. Oh.
Right?
Yeah.
It's an imprecise real.
Right. That is what I want.
Yeah. Yeah. And then my notion of convergence, my notion of continuity is giving you the behavior you wanted. Namely, if in your original space, you were able to converge to an actual point, then your function would converge to an actual real on the other end, because functions preserve points.
But in our usual analysis, the definition of continuity is necessarily punctual. So you define continuity in a point. And if you try to define continuity in an interval without defining continuity in a point, it's a mess.
Yeah.
So What is continuity if it's not continuity in a point?
But you can define continuity. You can define the pre-image of every open set is open. This is the function is continuous if that happens. Right. The pre-image of every open is open.
The image
the pre-image of every open is an open.
That is the textbook definition of continuity, actually.
Yeah.
That's what most people mean. But still pointed because pre-image is a pointed idea.
It's a pointed idea, of course, yes.
But the point, but the idea is that continuity has to do with preserving structure. And if you give me a structure in a different way, that doesn't mean I've lost continuity, right? So I don't have to think of it going point to point. I can think of it as structural preservation. And that's what I'm doing. And that's what frame theorists do. That's what
functions in topology.
exactly. They are structure preserving.
Continuous function is a function that lose open, and so some to say make how to say. So what is a discontinuous function?
So for example, one over x is a continuous.
No. What is a discontinuous function under this definition? So I say a discontinuous function is not continuous, but I want a positive definition of discontinuous function.
Well, that's difficult.
Your definition.
In locales, that's difficult because we have the morphisms of locales, which are the continuous functions. But for what you're asking me to describe something that isn't a morphism, what am I supposed to say to you?
Okay.
On the other hand,
Drew, can I comment on something?
Let me just make this one last point to Marco. If we use this as this is something like the discretization, almost making this into a discrete space. So what would preserving structure mean? This has no structure. So it's under no obligations. So this is the analog. I think this is going to be the analog of a general, perhaps not even continuous function. And what would it mean for it to be continuous? It would mean that it factors this way. That's the idea.
Valeria?
The other way.
Hi. Thanks, Drew. That was very interesting, particularly this idea of points being three different sorts of conceptions. That was cool.
Yeah.
But I don't have a real question. I just have two comments, two extra things to put on your reading list for the summer. One of them is the business of categorical probability, which I think you know has been extremely involved recently. And in particular, there was a talk last year by Alex Simpson in the Topos Colloquium. I don't know if you've seen this one.
Oh, I didn't.
So I recommend, because one of the things is very similar to what you was talking about. I mean, he started by saying that he wants to do synthetic probability, just like you want to do synthetic topology.
Like the people at Perimeter Institute are trying to do. Is that right? I think there are people at Perimeter that want that as well.
Yeah, I don't know enough. I just saw his talk, so I don't know enough about the stuff. But, on the same kind of vibe, there is also this business of synthetic differentiation, right? All this work that's happening on differential lambda calculus, differential versions of, so, kind of all this stuff seems to be things that you should look at with your local lenses, right? And I'm particularly interested in the differentiation business because apparently there's some connections with my own old work. But the business of the probability, Alex has some things about random variables and Dirac functions that look a little bit like your points, kind of.
Yeah, well, there was some earlier work that Alex refers to a little bit by a student of Mike Smith's.
Yeah, Claire Jones, right?
No, there's that. But I was thinking of this guy who, Alvarez Mania.
I don't
know. He wrote
that.
a nice thesis on measure theory from a domain theoretic point of view.
Right. Yeah. That's
And it really gives a really good picture of how all that stuff worked. It wasn't localic.
right.
It was pretty classical measure theory, but it was from the point of view of Scott continuous measures and things like that. So it was really a nice thesis.
Right. So you know, it's very different from some of the ways that people are doing things nowadays, because most of the stuff nowadays in categorical probability is using monoidal categories, not Cartesian closed ones, right? So
Right.
that's a very big difference in some ways. But
Yep.
but yeah, kind of lots of things to enjoy over the summer. So thanks so much.
Yeah,
So
that's
really cool.
sure. Yeah. Thanks a lot. And thanks for I didn't know that about Alex's recent stuff, so I'll look that
Yeah,
up.
just check. It was kind of June 2024, and you know, I think it's similar a little bit to what he then talked at Licks, because it's the same print.
It sounds like he's picking up this thread that he started a few years ago.
Yeah,
And
he did say
that's
to me.
encouraging.
He did say to me that he had kind of started it quite a long time ago, and he was still scratching the itch or something like that.
Yeah. Yeah, I'm glad to hear that. He's a smart guy, so he'll make progress.
Indeed, indeed. Okay,
Yeah.
bye. Have a good weekend.
You too.
Well, let's thank Drew again.